Welcome back to another episode of Data Dive, where we explore the fascinating world of data structures and storage engines. Today, we're diving into two popular data structures, LSM trees and D trees. We'll unpack their performance characteristics, discuss write amplification, and even touch on the rising trend of in-memory databases. So grab your headphones and let's get started. To kick things off, let's clarify what LSM trees and B trees are. Both are fundamental to how databases manage data, but they have distinct characteristics that make them suitable for different workloads. Generally, LSM trees excel in write-heavy scenarios. They're engineered to efficiently handle a high volume of writes. On the other hand, B trees tend to shine during read operations. So, if your application is primarily about writing data, LSM trees might be the way to go. But if quick data retrieval is your priority, then B trees could be a better fit. Now, here's the catch. LSM trees can be slower for reads. Why is that? It's because they need to check multiple data structures and SS tables, sorted string tables, at various stages of compaction. This complexity can lead to slower read performance. The takeaway here is that benchmarks can be quite sensitive to specific workloads, so it's crucial to test these systems under your unique conditions for a fair comparison. Let's delve deeper into one of the key challenges with LSM trees, write amplification. This term describes a situation where a single write to the database results in multiple writes to the disk over time. This is particularly concerning for SSDs, which have a limited number of write cycles before they wear out. The more a storage engine writes to disk, the fewer writes it can manage within the available disk bandwidth. This can create performance bottlenecks. Interestingly, LSM trees can have lower write amplification compared to B trees, depending on their configuration and workload. They write compact SS table files sequentially, which is typically much faster than the random writes often required by B trees. On the flip side, B trees can suffer from fragmentation, leaving unused disk space when pages are split or when data doesn't fit neatly into existing pages. LSM trees address this by periodically rewriting SS tables, which helps reduce storage overhead and fragmentation. This is especially beneficial for SSDs, where effective data representation can maximize read and write requests within the available I/O bandwidth. However, it's not all smooth sailing for LSM trees. Compaction, an essential process for maintaining performance, can interfere with ongoing reads and writes. Even though storage engines aim to perform compaction incrementally, it can still impact throughput and response times, particularly at higher percentiles of query response times. B trees, in contrast, usually offer more predictable performance. Another challenge comes into play when write throughput is high. The disk's finite write bandwidth must be shared between the initial writes and the background compaction processes. If compaction can't keep up with incoming writes, unmerged segments can accumulate, leading to slower read operations and potential disk space exhaustion. This is a crucial aspect to monitor in LSM tree implementations. While LSM trees and B trees are popular choices, they aren't the only options out there. In recent years, in-memory databases have gained traction. These databases take advantage of the decreasing cost of RAM, allowing for faster data retrieval since they don't need to access disk storage. In-memory databases can be categorized into two types: those that accept data loss upon machine restarts and those that strive for durability. The latter often employ techniques like logging changes to disk or replicating in-memory states to other machines. They're designed to serve reads entirely from memory, which can significantly boost performance. For instance, Redis and Couchbase are well-known in-memory databases that offer varying levels of durability while capitalizing on the speed of RAM. They eliminate the overhead associated with managing on-disk data structures, making them particularly appealing for applications that require quick access to data. Now, what about complex queries? Traditional indexes may struggle when you need to query multiple columns at once. For example, if you're searching for restaurants within a specific geographical area, a standard B-tree or LSM tree index won't suffice. This is where specialized spatial indexes like R-trees come into play, allowing for efficient multi-dimensional queries. These spatial indexes can handle complex queries, like finding all the restaurants within a rectangular area, much more effectively than traditional indexes. This capability is crucial for applications that rely on geospatial data, such as mapping services or location-based searches. Another intriguing aspect of data querying is fuzzy searching. Traditional indexes allow for exact key searches or range queries, but fall short when it comes to finding similar keys, like misspelled words. This is where advanced techniques come into play, such as those used in Lucene, which can perform searches based on edit distance, accommodating typos and variations in language. Lucene employs a sophisticated structure that combines an in-memory index with a sorted file for efficient querying. This approach allows for flexible and powerful text searching capabilities, which are essential for applications dealing with large volumes of text data. As we wrap up, let's reflect on the key takeaways from today's discussion. LSM trees and B trees each have their unique strengths and weaknesses, making them suitable for different workloads. Right amplification and compaction are critical factors to consider when evaluating storage engines, especially for SSDs. The rise of in-memory databases presents exciting opportunities for performance improvements, particularly for applications that require quick data access. And, as we've seen, specialized indexing techniques are vital for efficiently handling complex queries and fuzzy searches. Ultimately, the choice of data structure and storage engine should be guided by the specific needs of your application. Testing under real-world conditions is essential to ensure you select the best solution for your use case. Thanks for joining us on this episode of Data Dive. We hope you found this discussion insightful and engaging. Don't forget to subscribe for more deep dives into the world of data structures and storage solutions. Until next time, keep exploring and stay curious.